This is Lab 2 where we look at the motion of a falling object as it heads towards Earth. The purpose of this lab is to record and analyze the motion of a falling object to determine the object's position moving at a non-constant velocity. We'll first create a computation model that only uses gravity, and then create another computation model that utilizes both gravity and drag on the falling object using the turbulent drag formula. From there, we'll compare the two computational models to determine which one is more accurate in representing the tracker data. As looked at in the first lab, Newton's second law of motion, also known as the momentum principle, focuses on the behavior of an object when existing forces are not balanced. It states that the motion of an object is dependent upon the net force acting on the object and the mass of the object. The two equations that we looked at from the Newton's second law is the velocity update formula and the position update formula as shown here. Weight force is the force acting upon the object due to gravity, and on Earth, g is equivalent to 9.8 meters per second squared. The formula for weight is W equals negative mass times g times the unit vector. Drag force is the resistant force caused by the motion of an object through a fluid, and in its opposite direction of the velocity. In drag force, magnitude is proportional to the square of the object speed as shown in the equation here, where velocity is squared times the drag coefficient. In summary of the lab, we looked at and saw that the model with both drag and gravity was the most accurate between the two, and the model containing only gravity was not as accurate due to the exclusion of drag. Within the setup of this lab, I used a chroma sheet of paper as my object in motion and I dropped it from the height of my door. I then used my phone to record this where I included my tracker information. Here are some of the calculation variables used within this experiment. I calculated the mass of the sheet of paper, the length of the meter stick, the initial position of the ball, the final position of the ball, and the final observed time, which is 0.667 seconds, including with the mark frame, which is 60 frames per second. I utilized the final position of the ball to determine the drag coefficient, as you will see later on in the experiment. I positioned the coordinate plane at the center of the paper ball as shown in this frame. I then used the yardstick as a length of reference, as shown by the blue segment. The video on the top that shows the motion of the ball as it dropped from my hand. I can see throughout the video, the gaps between each time increment increases, showing that the velocity is increasing due to acceleration. The video was trimmed to show where the fall begins and ends right before the ball hits the ground. And as you see in the curve on the right, you can see that due to it not being in a straight line, the net force is not zero, and the velocity is not constant. This is the first competition model I created only using gravity. To begin, I stated the mass of the paper, then the position from tracker, and the initial velocity as well, which is 0. I then added the change of time, made sure it was very small, and made the acceleration due to gravity equal to 9.8 meters per second squared. I had defined the direction that the object is moving as well. I then added the weight force and the drag force to the code, and then incorporated the force net, which is just the net force equals weight plus the drag force. And I added the velocity formula, the position formula, and made sure to update the time throughout the loop. This video shows the finished code after this run. As you can see within the video, the ball is falling in the negative right direction. When comparing the first computer model and the observed model, you can see that the slope of the two lines are nearly the same, but after 0.3 seconds, the recorded motion begins to drift away from the curve of the computational model. The R coefficient of the paper ball motion captured by tracker is 0.997, which is nearly equivalent to the R coefficient of the computational model, just a little bit different. However, as you can see towards the end, there's a big deviation due to the error where the tracker point was determined and due to the fact that drag force was not included within the computational model. This is the second competition model that I created. This one includes both gravity force and drag force. For the most part, the code is completely identical except for a few parts. Right here, we added the drag constant instead of making it 0 so it fits the final position of the observed motion, and we did this using trial and error. I then added the equation of turbulent data, which is Fd equals bv squared, and then added the total net force, which is weight plus Fd. The second code is right here, showing drag in the positive direction and gravity in the negative y direction. After including the drag force of the falling ball, the curve between the computated and observed data is nearly the same, as shown in the gray and blue curves. The R coefficient of the computation model is 0.997, which is the exact same as the R coefficient of the ball captured by tracker. This data shows that due to the addition of the drag force and the gravitational force on the total net force, the second computation model creates a more accurate representation of the falling object. The motion of the object, however, was not perfect due to the possibility of other forces and interaction taking place in the motion that could have moved it to the x direction, and due to the short frame rate which was recorded, could not be as accurate as it should be. What does it mean? terminal velocity occurs when an object that is approaching Earth does not change the velocity anymore due to the gravitational force and the drag force canceling out. The model with both gravity and drag force showcases the beginnings of reaching terminal velocity because the slope flattened out at 0.4 seconds, showing that the object is now falling at a constant velocity. The net force of the object will now be zero, as shown in the graph here. If the object was thrown down initially, the terminal velocity of the object received will not change. The ball that is thrown down initially will receive a constant velocity faster than the ball as if it was dropped, but since both end up flattening out, the terminal velocity remains the same, as shown in the graph here. Within this lab experiment, we're able to determine the motion of a paper ball and compare it to a model that includes gravity and another model that includes both gravity and drag force. We determined that the model that includes both gravity and drag force is the most accurate due to the model containing more interactions with within the real world based on Newton's second law.